One tiny cocoon fits easily in the palm of a hand, yet it contains an immense chain of value capable of reshaping the global market. In an age where humans create materials from data and harvest energy from the wind, the silkworm continues to weave miracles in its own way. At first glance, this seems archaic compared to generating life in laboratories. But in reality, a sophisticated bio-industry is emerging across the still plains of China. Every process here is governed by scientific precision and strict industrial discipline. Could it be that the secret weapon of the future is being spun by this tiny creature? Modern technology advances rapidly around us. The answer is affirmative, as silk is no longer just a symbol of the past, but a material redefining the fabric of the 21st century. One can notice how nature and technology become one in this field, merging organic structures with engineering. From fashion to medicine, and from traditional materials to advanced biotechnology, the scope expands relentlessly. The potential locked inside grows with every analysis. But this is just the beginning. Thus, the insect quietly spins the foundation for a fascinating journey of innovation. 500,000 tons of plastic microfibers are released by the synthetic fabric industry each year. These microscopic particles seep into oceans, silently poisoning the world's water sources. Why then is China witnessing the powerful revival of a 5,000-year-old Silk Road tradition? At first glance, synthetic production seems superior in speed and cost. But in reality, the ancient method solves the critical issue of pollution. This shift marks a return to natural engineering. But this is just the beginning. The country produces more than 60,000 tons of raw silk annually. One can notice that this massive volume accounts for nearly 70% of global output. The sector generates over $5 billion United States dollars in export revenue. Millions of rural workers find employment tending to the cultivation process. The silk threads spun from the most common silkworm species, Bombyx mori, are as light as air. Yet, they are several times stronger than steel by weight. Unlike synthetic fibers, the material naturally decomposes without leaving behind microplastics. It is visible how these threads weave a nation's economic and cultural identity. The process is only gaining momentum. From high-tech factories to the runways of Hermes and Dior, China transforms this ancient fiber into a new symbol of the biomaterial revolution in the high-tech era. 20,000 square meters is the vast area covered by a single modern silkworm facility in the Sichuan region. These structures operate essentially as self-contained industrial ecosystems. Why invest in such heavy insulated roofing and integrated microclimate control systems for insects? To the uninitiated, the scale of protection might look excessive. But without this strict isolation, the delicate biological cycle would fail under external weather shifts, which is why the system maintains a stable environment year-round. Rows of multi-level rearing houses stand arranged in parallel lines inside. But this is just the beginning. One can notice how the interior organization resembles a sterilized data center rather than a traditional farm. Because the larvae are extremely sensitive, each room maintains a temperature between 25 and 27 degrees Celsius. Humidity is locked strictly at 80%. At first glance, setting these parameters seems simple, but in reality, digital sensors connected to a central data system must continuously regulate the atmosphere to prevent even the slightest fatal deviation. Automated ventilation fans rotate ceaselessly, driving air through the corridors with mathematical exactness. It is visible how every square meter accommodates 1,500 to 2,000 silkworms growing in perfect synchronization. Factors from lighting to air purity are calculated precisely within this pristine space. Sterilizing floors and real-time monitoring systems operate non-stop. The process is only gaining momentum. Thus, the facility functions as a large-scale biological laboratory, where technology and life move together in absolute precision. Billions of silkworms rely on a nutritional cycle calculated with absolute precision. In this closed production chain, the diet provided to the larvae is strictly controlled. Their only food is mulberry leaves, harvested from specialized farms located right next to the rearing facilities to ensure the highest nutritional value. One can notice how mechanical harvesters or farmers carefully select branches every morning. But this is just the beginning. Why do workers select only the middle and lower sections of the branches? To the untrained eye, the foliage looks identical across the tree. However, it is in these specific zones that protein and chlorophyll levels reach their absolute peak. Immediately after cutting, the raw material enters the processing area for sorting. It seems like a simple cleaning step, but in reality, the leaves must undergo gentle air drying with cool natural airflow. Silkworms never drink water throughout their entire life cycle, absorbing moisture exclusively through the plant matter they consume. The process is only gaining momentum. Even a thin layer of dew is visible as a threat, capable of causing fatal bloating or widespread disease among the larvae. Therefore, each mulberry leaf is treated as a standardized nutritional unit. This biological foundation allows the colony to spin the purest silk threads on Earth. 25,000 times its own body weight is the staggering amount of mulberry leaf a single silkworm consumes over a lifespan of roughly 25 days. To support this insatiable appetite, dried foliage travels rapidly to the rearing area, where millions of larvae enter a critical growth stage to spin the purest silk threads on Earth. Inside climate-controlled rooms, one can notice thousands of trays stacked in neat rows, each holding hundreds of larvae at the identical phase of development. But this is just the beginning of the care they require. Why is the foliage cut into strictly measured fractions depending on age? At first glance, it seems the hungry larvae would devour leaves of any shape without issue. However, young silkworms physically manage only soft fragments 0.5 centimeters in size, whereas mature ones require thick strips 3 to 4 centimeters long to stimulate production. Staff distribute the feed 4 to 5 times a day at fixed intervals, because precise timing synchronizes the metabolism of the entire population for uniform growth. It gets more complex further on. Automated microclimate systems adjust the atmosphere after every meal, initially lowering humidity to 70% to prevent the risk of mold formation on the organic matter. Then, the equipment gradually raises moisture levels back to 80% to facilitate proper digestion within the worms. Under the soft, diffused light of the facility, the mechanical hum fades into the background. The only audible sound remaining is the ceaseless, gentle rustling of leaves from the chewing mandibles. This delicate rhythm marks the steady creation of the material. 24 degrees Celsius is the precise temperature established in the rearing hall as the process shifts phases. Why is this specific climate strictly maintained? At first glance, the room seems to shift into a slower rhythm with a soft rustle, but in reality, the automated system stabilizes humidity at 75%. This balance allows the silk glands to function at full capacity without drying out. One can notice how the bodies of the silkworms turn translucent white, delicate as mist under the diffused light. But this is just the beginning. Millions of larvae prepare to spin their protective shells simultaneously. The camera glides along the multi-layered bamboo and plastic racks, where each insect secures itself firmly. They begin moving their heads in a graceful figure, 8 motion, to construct the casing. Liquid protein secreted by the glands solidifies instantly upon contact with the air. 10 microns is the thickness of the thread formed by this substance. 1 to 200 meters is the distance this single fiber can stretch. The weaving continues non-stop for 48 to 72 hours. It gets more complex further on. A sea of white cocoons emerges, rewriting the landscape of the rearing hall. Thus, each finished unit weighs just 2 to 3 grams. 2 to 3 times the strength of domestic varieties distinguishes the golden threads produced by the Tusa moth. While farms in southern China are covered in millions of shimmering white Bombyx mori cocoons, the northern regions quietly cultivate a different chapter of the industry. Why are these facilities designed as semi-open structures rather than fully enclosed halls? The infrastructure combines natural light with automated climate systems. This specific design recreates the conditions of a forest habitat necessary for the insect's natural life cycle. Moths preserved from the previous season are released onto hanging racks where they fly freely and mate naturally. But this is just the beginning of the reproductive phase. One can notice how the insects remain active inside climate-controlled cages, kept at 26 degrees and 70% humidity to maintain peak vitality. It seems like a hands-off process, but human intervention is timed perfectly. At first glance, the mating on the frames appears entirely natural, but in reality, farmers employ a specific technique to ensure success. After 3 to 5 days, workers gently shake the frames with bamboo sticks. It is visible how this motion disperses pollen to significantly increase fertilization rates. The larvae are then raised separately. Transition to the next level involves a strict diet. Because the larvae feed exclusively on oak, elm, or wild apple leaves, they ingest high levels of tannins. Consequently, these organic compounds give Tusa silk its characteristic golden hue and exceptional structural density. The fibers acquire a natural luster that distinguishes them from the white silk of the south. It gets more complex further on. 50 to 60 days is the duration of the Tusa growth cycle, which is nearly twice that of domestic silkworms. Unlike standard methods, these insects are allowed to complete their full metamorphosis rather than being harvested early, preserving genetic diversity and long-term sustainability. The dense fibers form what is revered as the silk of the forest, providing a prized material for luxury craftsmanship and art. "72 hours, exactly the time that passes after the silkworms cease their spinning work before the next phase begins. The ivory-white hue completely covers the rearing racks, shifting the entire farm into a different rhythm. Why is this specific waiting period strictly observed? At first glance, the cocoons appear ready for collection immediately, but the delay allows the larvae inside to settle, ensuring the moisture content drops below 12% for structural integrity. Farmers begin the first harvest only after confirming these precise conditions. One can notice how they carefully check each frame to ensure the hardness reaches between 3/10 and 4/10 of a newton. Without these parameters, the delicate 10-micron silk fibers risk damage during extraction. But this is just the beginning. In the past, separating 10,000 cocoons by hand required 8 hours of monotonous labor. Today, that effort has been replaced by compact mechanical systems. A hydraulic hoist with a lifting capacity of 300 kilos raises the spinning racks effortlessly. It lowers them onto conveyor belts moving at a speed of 10 meters per minute. Semi-automatic separators accept the frames without stopping to process the load. It looks outwardly aggressive to subject fragile silk to such force, but in reality, the system acts with jewelry-like precision. Using 80 units at 2 Hz of vibration and calculated air pressure, the machine separates tens of thousands of cocoons within minutes. The 10-micron fibers remain completely undamaged throughout the shaking process. Consequently, harvesting efficiency increases tenfold compared to manual methods. Waste drops below 2% as the cleaned cocoons collect in the receiving bins. The hum of machinery blends with the faint rustle of dry shells, marking the mechanical heartbeat of the modern silk harvest. 0.4 to 0.6 millimeters is the strict thickness standard for every cocoon shell selected for the high-grade silk production line. Why is such extreme precision required during the manual sorting phase? To the untrained eye, the trays arriving from the farm appear filled with identical white ovals, and the process looks like a simple visual check. But any deviation in the shell's structure will cause the thread to break during reeling, making rigorous inspection the only way to guarantee quality. Layers of cocoons are spread thin on long bamboo tables covered with fine mesh, where every movement demands sharp eyes and years of experience. Workers inspect the raw material under natural light to evaluate uniformity, luster, and surface smoothness, rejecting any piece that is not perfectly rounded. But this is just the beginning of the selection process. Immediately after sorting, the qualified cocoons are sent to the heat treatment area to halt the biological clock of the larvae inside. Because if the larvae mature into moths, they will pierce the shell and destroy the continuous filament, the life cycle must be stopped using steam heating, hot air drying, or immersion in water at 85.95 FN6. Each batch is gently stirred to ensure even heat distribution without deforming the outer silk layer. This step not only prevents metamorphosis, but also sterilizes and stabilizes the silk protein, keeping the inner fibers soft, strong, and long-lasting. One can notice how the dried cocoons are transferred to a row of warm basins releasing gentle steam. Here, the sericin layer coating the silk fibers begins to awaken in water, maintained between 65 and 90 degrees Celsius. A light stirring system keeps each cocoon fully submerged, allowing the shell to soften gradually. At first glance, the floating cocoons seem unchanged, but in reality, the surface becomes slightly elastic instead of brittle, signaling that the inner fibers are ready for the most delicate stage. The factory atmosphere now moves in harmony with the rhythm of steam and metal, blending the simmer of water with the steady hum of spinning reels. It gets more complex further on. In basins maintained at 90 degrees Celsius, slow rotating circular brushes begin the search for the silk's loose end. This thread is only 10 microns thick, making it almost invisible to the naked eye as the brushes tease it from the shell. Once the end is found, workers quickly guide it into the reeling machine, where synchronized drives pull the strands in perfect rhythm. Threads from 5 to 10 cocoons are combined, evenly stretched, and wound onto spools at a speed of 300 meters per minute. One can see how each rotation catches the light with a silvery shimmer, the fine silk flowing through rollers like liquid metal born from the breath of the cocoons. On average, a single cocoon yields about 1,000 meters of thread, and roughly 3,000 cocoons are needed to produce just half a kilogram of raw silk. The process is only gaining momentum as the threads move to the spinning machines. Spindles rotate at 6,000 to 8,000 revolutions per minute to twist the fine strands into a durable structure. In the quiet space, the hum of rollers and the soft hiss of steam fill the air as clusters of delicate filaments intertwine. At this stage, artisans may blend fibers from different cocoons to create variations in thickness, sheen, or distinctive patterns. Because silk possesses long, smooth fibers, it needs only a gentle twist, just enough to unify the strands while preserving the graceful drape. This contrasts with wool or alpaca, which require a tight spin to prevent breakage. The artistry lies in the twist ratio, determining the signature luster that makes silk one of the most elegant materials ever woven. When the spinning reels come to a stop, the silk's journey of refinement moves to the next phase. Transition to the next level. In basins kept at 60 to 70 degrees Celsius, a mild alkaline solution slowly dissolves the outer sericin layer. It is visible how the threads reveal a luminous, glassy core beneath the soft mist, feeling almost weightless and smooth to the touch. Freed from its coating, the silk awakens as a radiant material ready for color. The threads are taken to the dyeing section, where steam and herbal scents blend in a warm atmosphere. In deep baths maintained at 80 to 90 dexuxylene, natural dyes extracted from indigo leaves, pomegranate peels, rosewood, or madder roots slowly seep into every fiber. The silky bundles soak for 4 to 6 hours, gently stirred to let the color reach the core and create a clear tone. This ancient dyeing craft remains the soul of ikat and brocade patterns, where every shade is born from the earth. After absorbing the natural dyes, the shimmering silk threads move to the weaving area, the final stage of their long transformation. Depending on the purpose, the silk may be woven on handcrafted bamboo looms or industrial machines operating with millimeter accuracy. Every gentle pass of the shuttle serves as a pulse of creativity, turning fragile threads into flowing forms. In modern workshops, thousands of fibers move in perfect harmony under digital control, interlacing and shimmering under the light. Each strand becomes part of a larger pattern, fluid yet precise, uniting human skill and mechanical rhythm. The fabric is finally ready to leave the loom, carrying with it the legacy of resilience and elegance. One single continuous filament creates a material of exceptional tensile strength. Why does this organic fiber retain industrial significance in the era of heavy polymers? It seems obvious that synthetics are superior, but in reality, the protein structure created by the silkworm possesses physical properties that engineering struggles to fully replicate. But this is just the beginning of its technical potential. One can notice the smooth surface texture, which belies the internal structural resistance. The thread remains soft to the touch, yet withstands high mechanical loads. It bridges the gap between historical production methods and modern utility. Thus, the biological fiber establishes a functional standard for future materials.